In this lesson, we will showcase some of the more common DFX approaches. It could be argued that design for cost, design for manufacturing, and design for quality are all overarching approaches that move into and out of the approaches we will discuss. When we are performing corrective or preventative maintenance, our ease of completing the task boils down to time, material, and money. Ease of maintainability is a design feature that affects these factors. Use of the product helps us uncover opportunities to improve maintainability. Some guidelines for designing for maintainability are listed here. Note that many of these overlap with other DFX approaches. Standardization looks to minimize the number of different parts in the system. This reduces the number of parts we must maintain should they need to be replaced. Modularization addresses commonality in size, shape, and modular units. This facilitates uniform assembly procedures. Functional packaging groups related components of an item into a kit or package. Interchangeability allows us to exchange parts from unit to unit. We see this approach in automotive. How often can you find a component you need for a certain model car by taking it off of another model manufactured by the same company? Accessibility speaks to the ease of access and replacement. Malfunction annunciation is the signal that tells the customer that something has failed. When we apply the brakes on our car and we hear metal grinding, this is how we know that it's time to change the brake pads. Fault isolation is a means to localize failures should a cascade of failures occur. Identification deals with having a unique identifier for all components, such that documentation of corrective and preventative maintenance can be accomplished. If we monitor and track component performance, we may see trends that mandate changes in suppliers or equipment. Design for producibility seeks to pivot toward component parts that can easily and inexpensively be manufactured under high volume and quality conditions. Tolerance requirements would be aligned with production capabilities. Examples would be injection molding, stamping, extruding, and machining. Design for assembly seeks to ease the act of assembly, but also looks to minimize the number of parts. Deploy lean principles such that motions are simple and ergonomic, as well as minimize the number of fasteners required. It is really as much designed for manufacturability as it is designed for assembly. Many of the opportunities in assembly can be realized at the design stage. Remember that our first design is seldom our best. We must be prepared to iterate. Reliability is best facilitated through simplicity. Eliminate parts in ascending order of cost. In other words, aim to eliminate your lowest cost parts first. Design for reliability aims to provide the customer the best value for their money through maximization of the life cycle value and minimization of life cycle costs. Tools such as FMEA can be instrumental in this process. Design for serviceability is somewhat related to maintainability, but we will provide a unique treatment here. When we design for serviceability, we consider how easy it is to service the unit. Service can be due to routine maintenance or unscheduled service. Both generate costs that we should endeavor to eliminate. What tools do we need to service the unit? How many fasteners do we have to remove? How difficult is it to gain access to the defective component? Of course, reliability also plays a role in these questions. The more reliable a component is, the less likelihood that we will have to service the component. Serviceability can also be addressed in how we design the product. For example, do we design a washing machine with a pressure chamber to detect water level that must be accessed and cleaned regularly? Or do we look for a control solution to measure the flow of the water and discontinue the flow after a certain amount of time has passed based on the volume of the load? Improved service increases our customer satisfaction, reduces warranty costs, and improves our likelihood of a resale. Design for product retirement pertains to how the product will be reused, remanufactured, recycled, and/or disposed of. Environmentally speaking, landfills are getting closer and closer to capacity. Anything we can do to maximize the use of recyclable materials and minimize the use of scarce or toxic resources helps in our aims to minimize the long-term impact to the environment. Design for product retirement requires a long-term outlook. We must consider how to best disassemble and the percentage of materials designated to each final disposition. Remember, disassembly costs rise as the system is further disassembled. If groups of components are all allocated for the same fate, then this alleviates our cost to disassemble.